Thank you very much, Reinhard. So it's a privilege to be here, and I'd like to express my sincere thanks to the organizers for the invitation to be a part of this beautiful program, and also for the invitation to give this talk. Now, it is by now very well established through work of many people, several of which are present here, including my chair, that C-star algebras and groups can be very fruitfully used to study quantum correlations. And my talk will be in part about some aspects of the study of quantum correlations using C-star tensor norms. And the remaining part will be about the study of a class of quantum channels, unital quantum channels, the so-called factorizable ones, and their connection to the con-embedding problem. And I hope to be able to report on some new things, some of which are very, very preliminary, but nonetheless, we that are part of those think that it's a meaningful thing to look at. So quantum correlations arise naturally in this scenario of having a quantum system being emitted from a source, and two scientists, the two scientists that we've met many times in this meeting, Alice and Bob, residing in spatially separated labs, each receives a part of the quantum systems and perform a part of the quantum system and perform measurements on them. And let's just say that Alice and Bob can measure any one of k possible observables, each of them with m possible outcomes. In Vern's lecture, m was n, so that's the only difference. And we are interested in expressing these probabilities, namely these correlations. So the probability that Alice gets outcome A when measuring observable x, and Bob gets outcome B when measuring observable y. Now, for each observable that they are measuring, Alice and Bob get a projection valued measure, for short PVM, which is m tuple of projections on some Hilbert space. In some case, in some models, this Hilbert space can be a common one, such that these projections sum up to 1. And depending or according to the mathematical model that we choose to interpret this physical separation of the two labs, namely the tensor product formalism versus the assumption of commutativity of observables, the correlation matrix that we get belongs to one of the following sets. Now, I was lucky that in many ways that Vern Paulsen gave the talk before me. I also got to learn some new things from his talk. But for now, I will make use of the fact that he carefully described the two setups in these two mathematical models that we choose. And so I'm not going to redo that and just write down the sets of quantum correlations that we get in the two settings. So the first one, he denoted it by C sub QS. I just prefer the Q from quantum, so this is quantum spatial. So these are the correlations in the setting when we have this spatial tensor product model. And the second one is Q sub C, so this is in the case of the assumption of commutativity of observables. So that amounts to commutativity of the projections in the PVMs that, that Alice and Bob have at their disposal, and they live on a common Hilbert space. Now, the set Q sub C, so in the commuting case, is closed, and the fact whether, or the problem whether Q sub S is closed or not, that's a rather delicate issue. It will come back during the talk. So because we want to have a closed set, we take the closure of that and denoted Q sub A by meaning approximable correlations. And it actually turns out that for obtaining this Q sub A, it makes no difference if we work only with finite dimensional Hilbert spaces HA and HB for Alice and Bob respectively. It's not a completely trivial thing, but it is. And these sets QS, QA, and QC are nested like that. All of them are convex. And the question now that we want to look at. So it's this conjecture of Tyrrelson. So Tyrrelson in the 80s made a systematic study of quantum correlations and was led to believe that these correlations arising from the commutativity assumption are the same as the ones which are approximable by spatial ones. Okay, so that's Tyrrelson's conjecture. And as I made the point already from the beginning, sister algebras and groups can be used to study quantum correlations. And let me just prepare for what I will say related to that. So if one has sister algebras A and B, unital, then one can consider the algebraic tensor product of them and equip this or complete this with respect to certain norms in order to become a sister algebra. So here we have two very significant ones, the so-called minimal one, which is obtained, so the norm is defined using faithful star representations of sister algebras A and B on Hilbert spaces. And respectively, the second one, so-called maximal sister norm, where in the definition of the norm, this supremum is being taken over all representations on the same Hilbert space, but the assumption is that they have commuting images. Now, of course, if you see this for the first time, you may wonder for the minimal sister norm if this definition of the norm depends on the faithful star representations that are chosen, and the answer is no. This is a result of Takesaki, along with the fact that, in fact, this norm that we define that way is the smallest possible sister norm that one can put on the algebraic tensor product to turn it into a sister algebra. And respectively, the max norm, it's the largest norm that one can put on the algebraic tensor product to turn it into a sister algebra. So now we are going to denote the max and min tensor product to be the completions of this algebraic tensor product with respect to max, I said, and min respectively. And in general, these two sister algebras are different, and in fact, instances when these are equal can lead to very strong mathematical results. So let us concentrate our attention on a special sister algebra. So that is the universal sister algebra generated by a unitary representation of the free group on n generators. Here n can be any number between 2 and infinity, including infinity. So this is usually denoted by C star of Fn, and it's the so-called full group sister algebra associated with Fn. And 1993, in his famous paper published in Inventiones, Eberhard Kirchberg asked the following questions. Is it true that there is a unique C star norm on C star of Fn tensor with itself? Respectively, is it true that there exists a unique C star tensor norm on the algebraic tensor product of B of H tensor with itself? And he proved that if you mix the two, then the answer is yes. So namely, there is a unique C star tensor norm on C star of Fn tensor with B of H. And moreover, that the answer to question A is equivalent to having an answer for the embedding problem. So very deep results. And well, question B was answered by Marius Junge and Gilles Pizier in 1995 in the negative. And the proof uses a non-commutative version of the Grothendieck theorem, namely that if you have a CB map from an operator space into the dual of another one, then that factors boundedly through a Hilbert space. That was a tool in the proof. And so therefore, there isn't a unique norm on the algebraic, there isn't a unique C star norm on the algebraic tensor product B of H with B of H. And in fact, later, 2014, Pizier and Ozawa proved that there are at least 2 to the Aleph 0 non-equivalent norms on B of H tensor B of H. Okay. So now let's go back to our scenario with Alice and Bob performing measurements. So let's look at this group gamma, which is a free product of k factors of, so each of them being the cyclic group of order m. So remember the m and k came from that scenario, so it was k observables, each of them with m possible outcomes. One can realize the full group C-star algebra of gamma as a free product of C-star algebras. So that's the universal unital C-star algebra generated by unital copies, right, of this C-star, so generated by copies of C-star of Zm. So that's the one under or next to the star indicates that it's a unital C-star algebra, so unital free product. Okay, so one can realize C-star of gamma as this unital free product C-star algebra of those copies, and that C-star of Zm is in fact, say, if you wish, L infinity on dimension m, so that's a direct sum of m copies of one-dimensional algebras. So here these EJs are projections summing up to 1. And one would like to do some bookkeeping. So in the, yes, I was told that I should rather point here when I want to show something. So in this free product here, you see we have k free factors. So if we look at the xth one of them, then we are going to denote by EA decoration x above the projection EA given here in that free factor. So this bookkeeping is useful because then I can show you this result, which is work of Tobias Fritz, as well as independently. So I mean, maybe not specifically stated like this, but the ideas are there, as I said, a group of mathematicians, many of which are here. So that is Marius Junge, Navasquez, Carlos Palazuelos, David Garcia Perez, Volker Scholz, which is not here, and Reinhard Werner. So as far as I know, this paper was posted on the archive. So the paper discussing these things was posted pretty much the same day, 2010. Okay, so this work of theirs realizes these sets of quantum correlations in the two models, right? So the spatial ones, respectively, in the model assuming commutativity of observables, using states on the min, respectively, the max tensor product of C star gamma with itself. So that's the way that one uses C star algebras and tensor norms on tensor products of certain C star algebras in order to realize the sets of quantum correlations. Okay, so now putting together the work of Kirchberg together with Fritz, Junge, and all, and with a final contribution of Takaozawa in 2012, this beautiful theorem came out. So the following statements are equivalent. There is a unique C star tensor norm on C star gamma with itself for all m and k greater or equal to 2. So remember, the group gamma depends on the parameters m and k. If and only if there is a unique C star tensor norm on C star f infinity algebraic tensor product with itself. If and only if Zirelson's conjecture is true, that means that the set of approximable quantum correlations is the same as the set of quantum correlations under the commutativity assumption, again for all m and k greater or equal to 2, because these sets QA and QC depend on m and k, sorry, not m and k greater or equal to 2. Respectively, the Kohn-embedding problem has a positive answer. So that's the theorem. So now I just recall again the definition of these sets of quantum correlations. So QS collects the matrices, the correlation matrices, where so one uses this tensor product formalism. QC uses the commutativity of observables formalism. So recall that Q sub A was defined to be the closure of Q sub S. So now comes the next and remarkable breakthrough due to Slofstra in about July 2016, when he showed that for M and K large enough, the sets QS and QC are different. So if it turned out by some miracle that, now I have to concentrate, that Q sub S is already closed, then we would have an answer to con-embedding. There was a little bit of hope, at least on part of some of us. However, he came back March 2017 and proved that QS is not closed, again for M and K large enough. So what this means that this closure in defining Q sub A is needed if we want to have a closed set. And it also means that con-embedding still stands as an open question, so the game goes on. Okay, but so Slofstra's results. Okay, and I also wanted to say that we have seen in Vern Polse's talk very, very recent progress also in this sense. So if I understand correctly, Vern, Ken Dijkema, and a co-author have given a different proof of this result and improved on the order on M and K. So I personally look very much forward to seeing proofs of these things. Okay, so maybe now coming back to what I promised you, that I will show some very preliminary results on the analysis of this quantum sets of quantum correlations using C-star tensor norms on some C-star algebras. So this stems out of Brown and I being in Barcelona attending a program on C-star algebras at CERN, and I was giving a talk. I have to confess that at that point I was not aware of this. It was beginning of April. And Nate Brown was in the audience, and he was very intrigued about this result of Slofstra, and especially about the fact, what would this mean at the level of purely C-star algebraic. So given the fact that we have now these interpretations of the sets of quantum correlations that I showed you before, right? So what does it mean, these sets being different at the level of a purely C-star algebraic understanding of things? Okay, so then we started thinking, and we realized that one can formulate the problem more generally. So for arbitrary unital C-star algebras A and B, one can consider the following three sets of states on the max tensor product. So the first one is S max. So these are really all the states on the max tensor product of A and B. The second set consists of states on the max which factor through the mean, meaning that when you compose them with a canonical surjection from the max to the mean, then they become states on the mean. And the third set, which is the more mysterious of them all, collects all the sets, all the states on the max, which have this very special spatial form. So it's special form, which is a spatial one. So they arise using vector states that come out of, so S vector states coming out of representations, star representations of A and B on Hilbert spaces. So that's a set of states in the S max, and right. So maybe I should go back. So one can see that these sets of states are nested like this. All three sets are convex. S min and S max are closed, while S sub SP, SP from spatial, is weakly dense in S min. And the fact that the max and min tensor product of A and B are the same can also be expressed by the fact that the two sets of states, S min and S max, are the same. Okay, so as I said, the most, of course, these sets of states, S min and S max, have been investigated in many contexts, and many things maybe are known about them, but it appears to us that this set of states, the spatial ones, that have this very special form, it's a little bit more mysterious, and maybe at least to our knowledge, it hasn't been investigated very much. So a question that one can think about, and it comes out naturally, is for which C-star algebras A and B are these two different? And supposing that they are different, in specific examples, can one find concrete states that witness this difference? And at the bottom of everything, it's this question, how can one see that a state in S-mean does not belong, does not have this spatial form? Is there a criteria to decide? We found this to be very, very intriguing and very difficult. So on this slide, I'm going to show you the connection with the sets of quantum correlations. So one can realize, so if now one specializes again to A and B being C-star gamma, gamma is our group of before, and considers M to be the span of those projections carefully labeled so that things look good. Inside of the max tensor product, this is a finite dimensional object, operator space if you wish. Then the sets of quantum correlations can be realized as restrictions to M of SP, S-mean, and S-max respectively. So now the results of Slofstra come into play, for example. And so his 2016 result says that Q sub S is different than Q sub C. So you can see at the level of S-mean, S-max, and SP what that looks like. And then later, he also showed that QS is not closed. So what this means is that QA is different than QS, right? Because QA is closed, QS is not. And in particular, this means that S-mean and SP are different in this example. So what we have right now is a concrete example of a state on the maximal tensor product of A and B, C-star gamma with itself, which arises naturally from the left-right, so-called left-right representation of gamma that does not have, so does not belong to this SP set, so does not have this spatial form. And the proof, it's a little bit tricky, it's non-trivial, and it relies in part on the Ackermann-Ostrand result from 1974 that the max tensor product of the reduced group C-star algebras of the free group, but it applies here as well, contains the compact operators. And more than that, anyway. So, so this is a concrete example of something that belongs to S-max, but does not belong to this SSP. However, it was disappointing for us to realize that it doesn't really do anything. It doesn't shed any light on Cyrilson or Slofstra's result because we were disappointed to realize that when restricted to M, this does belong to SP restricted to M, which is QS. So yes, of course, we knew that S max is equal to S min, then that would really be something. But knowing that S max and S min are the same, this is equivalent to solving on embedding. So that is not the way to hope for anything. OK, so what I want to say is that these are very, very preliminary things, and perhaps they don't really shed any light on Slofstra's result or reprove or anything. But nonetheless, perhaps, in our opinion, maybe a better understanding of these sets of states would be meaningful nonetheless. And perhaps it would even shed light on Slofstra's result or reproving or whatever. But we believe that it's a meaningful thing to consider. OK, so now maybe it's time to start the second part of my talk. So I've been talking about con-embedding problem. I'd like to state it. So con-embedding problem that Alain Kohn formulated in his celebrated classification of injective factors paper from 1976 asks whether every 2-1 factor on a separable Hilbert space embeds in an ultra power of the hyperfinite 2-1 factor R. I'm not going to define these objects. Again, luckily, Reinhardt. And I think that also Doug Farenik defined the hyperfinite 2-1. And this is a very abstract formulation to many of us. But I'd like to give you a reformulation which has a much more concrete flavor, much more finite dimensional somehow. So this is due to Dykema and Yushchenko, 2009, when they considered for every n greater or equal to 1 the following two sets. The first one takes the union of all n by n matrices whose entries are second order mixed moments of unitaries coming from matrices of arbitrary sizes. And there is no reason to believe that this set is closed, so we take its closure because we would like to have a closed set. And Gn collects all n by n matrices whose entries are second order mixed moments of unitaries coming from arbitrary von Neumann algebras with normal faithful tracial states. And by a refinement of Kirchberg's argument from his celebrated Invenciones paper 1993, they were able to conclude that the Kohn-embedding problem has a positive answer if and only if these two sets, Fn and Gn, are the same for all n greater or equal to 1. This reformulation of the Kohn-embedding, well, has the merit that it has a more concrete flavor, but also will be very useful in what I will tell you a little bit later. So in our work in relating behavior of a certain class of factorizable or certain class of quantum channels to the Kohn-embedding problem. Okay, so what is a factorizable quantum channel? So first of all, I haven't written, but it's somehow put in the definition. A quantum channel is a unital quantum channel. So unital quantum channel in dimension n, that's my notation. Unital, completely positive, trace-preserving map in dimension n. And the notion of factorizability was introduced by Claire Delaroche in 2005. She was not working in quantum information. She was actually working trying to establish ergodic theorems for actions of free groups on non-commutative spaces. And it was a notion that arose in her work. It was done more generally for maps which are unital, completely positive, and state-preserving between von Neumann algebras. But I'm just going to restrict to this setting, which is our setting here. So for quantum channels, factorizability amounts to the existence of a von Neumann algebra n with normal faithful tracial state psi and unital star homomorphisms denoted alpha and beta that go from the n by n matrices into this tensor product, Mn tensor n, such that T is realized as the adjoint of beta composed with alpha. Now, this adjoint is to be taken in the appropriate category, so completely positive, state-preserving in general maps. But so maybe this looks very abstract. First of all, I'd like to point out that these star homomorphisms have to, so it follows that they have to be, right, so necessarily are injective and trace-preserving themselves. So how can we maybe a little bit understand better, just right off the definition, this notion of factorizability? So what you have, it's like this. You have an embedding of the first copy of the n by n matrices, and one can even take the canonical one. So matrix units go to matrix units tensor identity. So alpha can be taken to be the canonical embedding of Mn into Mn tensor n, into the first copy there of the tensor product. And for the second one, we have to use beta. So this beta goes from Mn into this tensor product. And what we do is we take the conditional expectation of this Mn tensor n onto the image of beta. That's basically the adjoint. So you obtain T by doing alpha followed by this conditional expectation. Okay, still maybe not very illuminating, but it gives a little bit of the idea of what's going on. And the question that Claire posed then, she would have liked every Markov map that she was working with to be factorizable in this sense. So she asked, is every such map factorizable? So I'm going to ask the question here in this setting of unital quantum channels, is every unital quantum channel factorizable? So right off from the definition, we can say something. We can say that automorphisms of the n by n matrices are factorizable, with n simply being equal to the complex numbers. An automorphism of the n by n matrices, it's conjugation by unitaries, that is why. And the set of factorizable unital quantum channels in dimension n is convex. Therefore, it contains the convex Hall of automorphisms. And it is also closed, therefore compact. And in trying to understand Claire's question, together with Uffe, some time ago, we came up with this characterization of factorizability in every dimension. So this was specifically for unital completely positive trace-preserving maps on n by n matrices. It's not more general than this. That says that factorizability amounts to the existence of a von Neumann algebra n with normal faithful tracial state and the unitary in the n by n matrices over n, such that the map has this form. And in this case, we say that T exactly factors through Mn tensor n, or it has an exact factorization through n by n matrices tensor n. And I'm happy that Reinhard is here. He actually came up with this colorful interpretation of factorizable maps, colorful to me, I don't know. So it says that factorizable maps are obtained by coupling the input system to a maximally mixed ancillary one, so this n is the ancilla, executing a unitary rotation on the combined system, and then tracing out the ancilla. So that's what the factorizable map is. Okay. Now, Claire's question was, are there non-factorizable maps, or is everything factorizable? So using that characterization of factorizability, we obtained this sufficient condition for non-factorizability, namely that if you write your quantum channel in Choi canonical form, so that means that this, should go back here. That means that these Krauss operators are chosen to be linearly independent, and the number of them, the so-called Choi rank of the map, is greater or equal to 2. And moreover, that set is linearly independent, then we get a non-factorizable map. And with a little bit of, maybe I shouldn't show this, with a little bit of inspiration and luck, as always, using these three matrices in dimension 3 as Krauss operators, they satisfy the conditions in the proposition. We obtain the first example of a non-factorizable map. It's not an exotic map. It's actually the so-called Holevo-Werner channel, W3 minus in dimension 3. Yeah. So I don't know if it is correct to say, but I've been told that the Holevo-Werner channel often come to the rescue when it is about finding counterexamples. So they did their job this time as well. So now I think it's natural to ask, so the definition of Claire contains that factorization through a von Neumann algebra. So it's a very intriguing question. What kind of von Neumann algebras are needed? And do we really need to use von Neumann algebras? But the first question that we somehow looked at is what happens if the factorizable map exactly factors through something that is embeddable into R omega, so coming close to con-embedding problem. Can we characterize those that factor through something that is embeddable into R omega? So here is the result that this happens if and only if the map T can be approximated in CB norm by a sequence of unital quantum channels which factor through matrices. So it will be Mn tensor sum matrix algebra. And if and only if the given channel has a certain asymptotic behavior when tensoring with a completely depolarizing channel. So that's condition 3, which says that in the asymptotic limit, tensoring T with a completely depolarizing channel really takes you to the convex Hall of automorphisms. It's not a difficult proof, but I don't want to give many details here. I want to mention that, based on this theorem, we can actually find a reformulation of the con-embedding problem, which is that the con-embedding problem has a positive answer if and only if every factorizable map satisfies one of these three conditions for all n greater or equal to 3. I will give some lectures sometime starting in mid-October, and I will include proofs for many of these things, including this one. But I just want to tell you that the key tool that it's used in it, it's this reformulation of the con-embedding found by Dykema and Yushchenko. And the fact that, so if I go back, so the reformulation of Dykema and Yushchenko is that these sets Fn and Gn have to be equal for all n greater or equal to 1. And so how do we relate this to factorizable quantum channels and so on? Well, it's something that we have proven with Uffe, that the set Gn actually consists of n by n matrices whose associated Schur multiplier is factorizable. So that's the connection with factorizability that we'll be using. Plus a different equivalent characterization of factorizability, which I didn't want to write down because since I'm not giving details of the proof, it would have just taken time. But that's how this reformulation of Dykema and Yushchenko becomes amenable to our analysis using factorizabilities through the interpretation of this set Gn. Okay, so so this is yet another reformulation of the con-embedding problem. Every factorizable map, in every dimension, every factorizable map, okay, number one, that's clear. If it's factorizable and con-embedding holds, then it has to factor through something embeddable. But it's perhaps the interesting thing for people in quantum information is this asymptotic behavior of the quantum channel. So tensoring with a completely depolarizing, which to people not knowing very much about that, such as myself, it would seem that really destroys a lot of the information about the channel, but instead it doesn't. So tensoring with a completely depolarizing somehow in the asymptotic limit makes the channel to be a mixture of unitaries. Okay. So now in the last less than 10 minutes, I'd like to tell you about some things which are recent. So again, I think it's a very natural question to ask what kind of things you can factor through, and it's been asked a lot by many people. What kind of things can we factor through? So this is a new result that in each dimension one can find a channel. In fact, it is a convex combination of automorphisms which does not exactly factor through matrices. And I put above a result with Uffe much prior to this, saying that so if T is a convex combination of automorphisms, then it factors through Mn tensor something abelian, so L infinity. But in fact, this is a characterization of elements of the convex hull of automorphisms. So T is a convex combination of automorphisms if and only if it factors through Mn tensor something abelian. However, one has this result, which I stated here, that you can factor through maybe even, and that could even be finite dimensional, but it cannot always be a matrix algebra. So that's the meaning of this theorem. And what this theorem is based on, it's the following proposition, which can be done more generally, but just for the purpose of this talk, I wanted to leave it at the bare minimum of a statement, which says that in dimension n greater or equal to 3, if you have unitaries, u and v, and a t between 0 and 1, you can define t to be a convex combination of add u, conjugation by u, and add v. So this will be a convex combination of automorphisms. And if we assume that the set consisting of identity, u star v, and v star u, it's linearly independent, then t exactly factors through Mn tensor mk for some k, if and only if t belongs to 1 over k times z. So the point is that we have to find in this algebra here, so as I said, it can be done more generally. You have to find in this algebra here projections of trace t. That's why the restrictions on t looking like this. And it can be done with more than 2 unitaries, so there are variations of this, or I don't know, extensions of this if you wish, but this already, so this proposition already proves this theorem, because if you choose t to be irrational, then And also, I want to say that this condition that, that you can find unitaries in any dimension n satisfying this linear independence condition can be done in every dimension. So then the hypothesis of the propositions are satisfied in every dimension, and we can do it. So what this means, it means that we can say something about convexity of sets of unital quantum channels which factor through Mn tensor a fixed matrix algebra. Namely, so if you take K fixed, then the set of unital quantum channels in dimension n, so here n is greater or equal to 3, which exactly factor through Mn tensor Mk, this set is not convex by the result of the theorem. It is also, but it is closed. It's closed, that's a compactness argument, so it amounts to the fact that the unitary group in Mn is compact. And the second thing is, if we look at the set of unital quantum channels which exactly factor through Mn tensor Mk for some k, this one again is not convex by the same theorem, but it's not closed either because the closure of this set is convex. So if it were to be closed, then the set itself would be convex, right? So, so the closure of this is convex. That is because of the previous result. Right, this one. So the closure of things which approximately factor through matrix algebra, it's the ones that factor through something embeddable into R omega, and that is a closed set. So it's a combination of these things. So coming back to these results on convexity, right? So if you do it for fixed k, the set of maps which exactly factor through Mn tensor Mk is not convex, but it's closed. If you let k vary, then neither convex nor closed. So similar arguments, convexity arguments, lead to the fact that for any n greater or equal to 3, the set of unital quantum channels in dimension n, which exactly factors through Mn tensor some finite dimensional C-star algebra, is convex. And we don't know if it's closed. So this I'd like to pose as a problem. And there is a meaning to this problem, so it does something for us, knowing the answer. Because if the answer is yes, then it means that it turns out that every unital quantum channel which has an exact factorization through something embeddable into R omega, it will in fact factor through a finite dimensional C-star algebra. So, you know, it will not solve con-embedding by any means. It doesn't get any close to that, but it will somehow add to our understanding of factorizable channels, like what can they factor through. And I think it would be very natural to expect, maybe I shouldn't be misinterpreting what I'm saying, but one would expect factorization through finite dimensional objects. One would expect it. But of course, if you want to expect that for everything, then that's con-embedding. So I think this is a little bit or a lot more modest than attempting to solve con-embedding. It will just bring some light on the structure of factorizable channels. And of course, if it turns out that con-embedding is true, then what this would mean, in case this set is closed, it would mean that indeed every channel that is factorizable factors through something finite dimensional. We cannot hope always for matrices, but we will have this. So I think it's a nice problem to think about. I don't know the answer to it, and I'll end here. Maybe a little bit earlier, but thank you. Finite factor. I think the interest for me was looking at tensoring with finite dimensional objects, because I thought it would be natural to have that kind of statement. And when does that happen? I don't exactly know when it happens, but that's why investigating this. So yeah. But of course, one can ask a variation of questions like this. So maybe that's another one to ask. But yeah.
And also in that regard,
Yes.
Instead of when you're tensoring with mn tensor mk is a factor. So I'm just wondering if that has any role in whether the Markov map or the quantum channel is extremal.
It's very difficult to analyze or to characterize the set of of things that factor through mn tensor mk. Right now I don't know that. I think it would be very nice to have such, but I don't know. There are many related questions, none of which is really getting close to the fire of con-embedding, which are very nice to look at. So, but thank you for all of this. Right now I don't know, and these are things that I would like to think about in the 2 months to come.
There was at least another question there.
Yeah.
Marius first, maybe. Yeah.
So, do you know some algebraic properties of certain classes of factorizable maps? I think, square roots, or, it's the product of two factorizable maps. I'm asking because there's a slight relation to primitive channels, which came up in David's talk.
Okay, I don't know what the channels are. Maybe we can talk about.
I mean, the question is whether if you have factorizable channels, a square factorizable or a square root.
I think there are some results that we already have with UFE, so maybe we should look at those to see if that's something that you would be interested in. But systematic study of such, that I don't think, but just some concrete examples when things don't happen, I think, yes. And they are related, so this factorizability also can be phrased, Claire's factorizable, and I think there are, in terms of having a dilation, and I think that in that setting one can say a little bit more about that, not necessarily systematically, but in certain examples. Yeah.
Yes.
I think Claire at some point talks about factorizations that so that the down or up map is a special type or have a special type of properties, and she relates that to ambiguity type questions. So you are not considering factorization so that the down or up map has a special form or special property?
Not necessarily, but I think that in my lectures I will show concrete examples when you consider them specifically of certain types, and then you get, say, right away the factorizability, say, of the completely depolarizing channel, or showing that you can have very unrelated things you can factor through. So yeah, it leads to different algebras that you can factor through, for example, if you can factor through. Or so I think, yeah, these are things that make a difference. Yes.
In our work on embezzlement, we showed what embezzlement is really about. It's about the difference between the states that are spatially realizable and the states on the min-tensor product.
Really, you are getting close to something
exactly,
hot. Okay.
Exactly, embezzlement is exactly that phenomenon. You have a state on the min that cannot be represented spatially.
And you have concrete ones.
Yeah.
Okay. Then I think.
In fact, for C-star algebra, the complete answer is known, what is known to me, that this spatial space is not closed if and only if one of C-star algebra is type 1. All other cases you can find.
Let me put the slide so that at least this one, right? Mm-hmm. Yeah.
So SSP is equal to S min if and only either A or B or both are type 1.
Okay. So this is a known result, or it's known to you?
It comes from the representation say of the CAR, and it's just any non-type 1 is CAR is a sub-portion. And the proof is same to your proof, that the left action, right action CAR algebra and take up twice, then this is not spatial. And this leads to any algebra which contains CAR as a sub-portion.
Ours is the more subtle thing where we have an SSP restricted to a finite dimensional subspace, and there's no.
Yeah, this is also.
We have something in S
different.
Restricted to a finite dimensional subspace, and any extension can't be spatially represented. So it's we show an S min M is not equal to an S min M. For
So this is actually your approach to Slofstra's, is it?
With a Brown algebra, tensor
Uh-huh.
Brown algebra. That's where the Gauss stuff comes from. Stuff that Gauss oftentimes comes from.
Okay. Uh-huh. Well, so as much as somehow Michael was against me discussing these things because they are very, very preliminary, and as you can see, we don't have very much to show, but I'm glad I did it because it gave rise to this suggestion.
That's what talks are also for, right? Are there more remarks or? Yeah?
Just a question. I mean, in your final question, some set being closed, which
yep.
is exactly what kind of Slofstra showed, that it's not closed in the totally different context of factorial, but both are essentially equivalent to or are related to convexity. So do you expect to use, or that these Slofstra's ideas could be used
here?
in that problem? In
this?
Exactly.
I didn't think about it. No, I had no thought of relating this to Slofstra, but
Because I guess the I mean, how you use embedding here is via this like
yeah. But in some sense, I mean, as I'm trying to really think very hard that this is not about con-embedding. This is just something
but the closure
smaller.
Of quantum correlation is in the end also not related to quantum. So some set being closed, and I'm wondering whether.
Don't know. So yeah.
But okay, that's something because I would like. Okay.
Right. So I mean, when I say I don't know, then I really don't know. I don't have. I'm really bearing a lot here. I don't have an idea on how to whether this would be true or not, or how to. But thank you for suggestions.
Any further questions? So then that doesn't seem to be the case. So thanks again.